guess we'll get started. So, welcome to the HIIT Special Seminar. And I have the pleasure to introduce our speaker today, Arijit Shaw, who is a final year PhD student at the Chennai Mathematical Institute, where he works on the field of automated reasoning. And basically, the floor is yours, Arijit. So,
Hi.
share your slides and continue.
Sure. So, yes, you can see my screen, right?
Yes.
Okay.
Yeah.
Okay. So, thanks, Yoho, for that nice introduction. So, let's get started. My name is Arijit Shaw, and I'm a PhD student at Chennai Mathematical Institute. And what I'm interested in talking today is my work in automated reasoning, specifically in the problem of quantitative automated reasoning. So before I dive into the exact problem statement, let me tell you three different problems that we can solve if we solve this problem of quantitative automated reasoning. So the first one is network reliability. So our society is more and more being dependent on different types of networks. For example, the road network, the power distribution network, water transmission lines, and so on. And each of the components in these networks are susceptible to some kind of failure. And these small failures can cascade to a large failure in some scenarios like a natural disaster. As a society is very much dependent on these networks, we are interested to know that what is the probability that some part of our countries will be disconnected, like it can face a blackout. The second problem is a probabilistic model checking. So we are moving towards autonomous systems quite a bit nowadays. We have these autonomous driving cars, we have sensor-driven flight control systems, and so on. And all of these systems are autonomous systems which depend on some kind of sensors input. And the sensors input can go wrong with some probability. And as these systems are critical, we want to know that in how many cases a false sensor input can lead to a catastrophic failure, let's say within a flight. The third problem is fairness verification for machine learning models. So we are employing these models to verify to take very real life decisions. For example, whom to hire, whom to give a loan, and so on. And in these cases, we want our systems to be fair to all different communities. So given an algorithm, how can I verify that that algorithm is really fair to everyone? So these questions have one recurring theme, that these require you to reason over the whole system. And the domain of automated reasoning actually work well in these kind of questions. So in case of automated reasoning, you are given a model and some specific properties. And the central question that is asked is that whether it is always the case that my model satisfies this property. So you can ask the contrapositive that whether it is the case that there is a solution to this formula that M and not P to be true. So what people do is they use these tools called satisfiability modular theory solvers or SMT solvers, and they can handle these kind of questions very efficiently. So many of you might have already used some tools like G3 or CPC5, which are pretty good at handling these questions. And these are not only academic tools. For example, AWS makes 1 billion SMT queries a day. So what is this SMT? So let me give you a very small example. So you have a variable X, which can take a real value numbers. And you have this constant that X is greater than 5 or X is less than -5. So you can say, okay, if I assign X to 6, then this formula is satisfied. That's good. But now if you add one more constant to it, that X squared is less than 10, then if you look at it for some time, you will realize that there is no such assignment to X for which the whole formula gets satisfied. So this is an unsatisfiable formula. So in SMT, you can encode all different kind of questions where these variables come from different domains. We call it theories and we encode this kind of satisfiability queries. So in SMT, your theories can be real arithmetic, integer arithmetic, bit vector, strings, floating points, and so on. Basically, whatever you need to encode different reasoning scenario. So you have your you encode your theory constants like theory atoms and connect these theory constants via arbitrary Boolean connector. And the whole thing will consist of an SMT formula. So even in the Boolean setting, the problem is NP complete. So SMT problem is in general NP hard. So it is not very common that you will have a very efficient algorithm for SMT. But as I told you that there are very good tools now, which can work very well for some specific class of problems. Now, as this is a case that we are solving this SMT queries efficiently, it is possibly a good time to look questions which are lies beyond satisfiability. And also, if you look at the problems that we are trying to solve now, that network reliability, probabilistic model checking, fairness verification, these are not really a yes-no question. In these cases, you want to talk about some probability. You want to talk about the total solution space. And for that, we will require something as a measure of this solution space as a measure of this SMT solution space. So what do I mean by that? Let me give you an example. Let's say you have these three constants that x is greater than equal to, y greater than equal to 2, and x plus y less than equal to 6. Now, how many solutions are there? So that depends on what is the domain the variables are coming from. So if x and y are integers, then you can see that you have 6 pairs of x and y values for which this set of constants gets satisfied. So the measure of the solution space here will be the number of solutions, which is 6. Now, if you have a continuous domain, like your variables are coming from the theory of real arithmetic, in that case, you don't have these discrete solutions. And in this case, you want to compute the volume of this space. Like in 2-dimensional, you want to compute the region, like the area of the region which is covered by these 3 constraints. And that is basically the area of the triangle, which is basically 2. So we want this kind of measure in case of SMT. And this measure can also be generalized with arbitrary weights. For example, in case of discrete domain, we can have a weight for each assignment, and the weight of the whole formula will be the summation over all weights. Similarly, in case of continuous domain, the measure will be the integration over the whole solution space. Now, let's go back to our actual problems that we are looking at. So how do you solve this problem of network reliability with this SMT measure? So let's say we are given this input as a graph where you have set up vertices as is. We have a set of source nodes and a terminal node. For each vertex, you have some kind of power generation and requirement. And for each edge, you have a failure probability and on some limit that says what is the limit for that the maximum power that can flow through that edge. And you want to know that what is the probability that at this terminal node T, the power requirement is satisfied. Right. So in this case, you want to look at all possible subgraphs of this graph for which the power requirement is satisfied. You want to compute their individual probability and sum up their probability. And that will be the probability question that we are trying to solve. Now, if you look at it for some time, you will realize this is the exact problem we want to solve in case of SMT measure. So this problem can be reduced to a SMT measure problem. What about the second problem, the probabilistic model checking question? So in this case, you can model it as a discrete time Markov chain, where you have a set of states, a horizon, and transition probabilities. And you want to know what is the probability of reaching the target states within this horizon H. This is again a similar type of SMT measured problem, and you can encode it using this count theory of bit vectors. For the third one, on the fairness problem, you have a classifier, you have some kind of population model, you have some sensitive attribute, and you want to know that how often this our classifier M favors the group A. To compute that, you need to look at the probability that given this sensitive attribute, how often this classifier returns true. And if you look at this probability for each group and you give a similar result, then you can say that the measure is like the algorithm is fair. So the key takeaway from the last 3 slides was that for each of the 3 problems, you have to encode it into different theories, and accordingly, the problem will also change. And what we realized is that we need many different techniques to solve each of the problems. So I have a set of works and some more work for this SMT measure problem. And that has with all of this, I have a large framework to handle different kind of SMT measure problem. So today, let me tell you briefly about one of these. That is this volume computation work for real arithmetic formulas. So this paper was published last year at CARE, and it won the Best Student Paper Award. So first of all, let's look at how the solution space looks like. So remember, in case of real arithmetic, our boundaries are linear hyperplanes, but we have this arbitrary Boolean connectors. So it can be the case that the solution space is non-convex. And this non-convexity is the source of the whole difficulty. So what we want to do is, we given this polytope, like this solution space, we want to decompose it into polytopes, for which we know how to compute the volume. But the problem is, once you decompose it into polytopes, we have this intersecting region. So we want to compute the union of the volume, which we do not know how to do efficiently. For that, we discretize the solution space. So basically what we do is we take a lattice space which is fine-grained enough so that there is a relation between the volume and the number of lattice points inside this polytope. Now, once we have discretized this space, we use a set union type algorithm to handle the union of these lattice points. So we have a relation between the number of lattice points and the volume. So from the from an estimation of the number of lattice points inside the whole solution space, we can compute the volume of this whole solution space, which we want to compute. So we can show that using this algorithm, we can achieve an estimation of the volume with theoretical guarantees, basically back guarantees. And our algorithm runs in polynomial time, where the polynomial has this number of decomposed polytopes inside it. This is not only a theoretical algorithm, we also implement it in practice. So we had a couple of tools, which was the current state of the art. And out of a benchmark of 1100 instances, the baseline could have solved only 140. When we implemented our algorithm, we could solve almost all of the instances. So this TTC is our algorithm, and it solves almost all of the instances. So here is the cactus plot, where in x-axis we have the number of benchmarks, and the y-axis we have the runtime. And it shows that we have seen a significant jump in performance from the previous state of the art and our tool. So I was telling you that we had to make all different tools for different SMT measure problems. And for each of them, we have seen similar improvement. So I was telling you the result on volume computation, where we saw a jump from 140 to 1100. We have similar jump from this hybrid formulas, function counting, and bit vector model counting. And we are not only these are not only academic or paper tools used in papers, but people are also using it. For example, from someone from a chip design company in San Francisco Bay Area is using our tool, and they're very happy to have this tool in practice. So these are how they are working in practice on downstream tasks that I was telling you. So for the network reliability problem, that is basically our problem one, we have work in submission where we saw that the existing tools that could solve instances with number of vertices around a few hundred, and our tool can scale up to 40,000. And on the probabilistic model checking, the existing probabilistic model checkers that could solve instances of roughly of size 30, and our tool can go till 770. So we are seeing an impact on downstream tasks as well. So let me take a step back and tell me about the overall research overview of what I have been doing till now. So I have been telling you my results on different development I have been doing in SMT measure. I have worked a little bit on SAT solvers, and I have won some medals there as well. And one of the key challenges in developing these tools is that these problems that we are handling are really hard. But our tools can handle those really well because we have very efficient heuristics that works underneath. But on the benchmarks where we cannot solve these problems, there is a very little understanding why this doesn't work. So I designed a framework based on causality, where we try to understand, we make a rigorous framework to understand why these SAT solvers work and why they don't. I made a framework to understand model counters well. I am also organizing this international model counting competition for last 3 years, which also helped me to understand this, where instances they are coming from and how the tools are performing. On this based on this understanding, I try to develop more tools, and I try to based on that developed tools, I want to apply those in practice, like the problems of network reliability or this probabilistic model checking. So what do I want to go from here? So I want to continue my research on these 3 different thrusts of understanding, development, and application. And I want to extend my research in all 3 directions. On the development side, our tools are currently scalable for medium-sized grids, medium-sized model checking instances. To handle really very large-scale industrial instances, we also need to make them scalable to even larger instances. So our tools are currently doing this measured problem, but there are very interesting related quantitative reasoning problems, for example, optimization and sampling. I also want to extend our framework to handle these problems. I designed a framework to understand this causal relation between heuristic and the solver's performance. I want to use that to make a framework where we automate the development of solver heuristics. On the application side, I have many things in mind, but the one I am particularly interested in is this domain called logic-based learning. So let me tell you quickly about 2 specific directions that I really want to pursue in the next few years. One is this logic-based learning. So in logic-based learning, people use automated reasoning to learn rules from a few examples. And that solves 2 key problems in statistical machine learning that we all use. That in statistical machine learning needs a lots of data, and it is not generally very explainable like the models we learn. And this logic-based learning is used in many different scenarios, like the drug discovery and so on. And in these cases, the interesting question is active learning, is to make a new query and learn. Basically, like you are doing an experiment and learning from it. So the question becomes what query to make. And what I propose here is that counting can give you an answer. So let's say if this is the hypothesis to our robot, that this is the set of all hypotheses from which we want to find one hypothesis which is true. So the key problem is that this hypothesis space is very large. So we want to prune it. So we can add queries to it. So let's say we model it with a formula phi. Now we make a query Q. So it prunes half of the space. Or we can make a query not Q, which prunes remaining half of the space. So this is a good query because we can prune almost half of the space by whether the experiment comes true or false. So to understand whether a query is good or not, counting can give you a good answer by giving you how much hypothesis space you are really pruning. So I plan to work with Andrew Cropper from University of Helsinki. We have talked a lot about what we can do in this domain. The other thing I am interested in is the problem of optimization, where we have these great optimization solvers like Kurobi or Simplex, but they have some problems. And decision diagrams often help in these cases. So we have also used the decision diagrams in counting problems, but we use them in much richer forms. So with Matti Visalo from University of Helsinki, I have been talking about how we can use these decision diagrams that we use in counting in optimization to make optimization more efficient. So these automated reasoning tools are very general purpose, and I will be very happy to talk to you regarding what kind of applications you have, and we'll be very happy to collaborate. With that, I would like to conclude. I would like to thank all my collaborators, without whom none of this work would have been possible. And thank you all for attending the talk.
All right, thank you. We have time for some questions, so just show your hand and if you want to make a question. Maybe I'll make one question when others are thinking. So in your volume computation example, could you give some intuition that why this kind of making this kind of lattice of points, what you proposed, is more efficient than having some kind of geometrical algorithm that would track these shapes of these polygons that you are considering here. So where does the difference come from?
Yeah, so the key challenge possibly here is that we are looking, the region is constructed by these polytopes which are intersecting, right? And in a practical instance, there can be multiple such polytopes which are intersecting. And when you have lots of these polytopes intersecting, then there can be a huge intersection. So if you want to decompose it into disjoint polytopes, then there will be exponential number of such polytopes. So if you disjoint it into decompose it into disjoint polytopes, compute each of them and sum up, then it works. But the key challenge is that you will have a possibly exponential number of such polytopes for which you have to compute the volume and sum up. So what distinguishes our approach is that we do not decompose into disjoint polytopes. We can handle non-disjoint polytopes. And generally, it is the case that the benchmarks have this intersecting non-disjoint type of polytopes, which we can make use of.
Okay, thanks. Any questions from the audience?
I have one question, briefly.
Sure.
Arijit, you had a slide where you had the fragments, the theory fragments, and then the algorithm. You go to that slide.
Like this one?
This one, yeah. Could you, at a very high level, explain why the different theories need different algorithms and what, if there's any, are they completely different, the algorithms? Or are they very similar in how they approach?
Okay.
And how they work, sorry.
It's a very nice question. So the case is like I was telling you about the second algorithm, right? The volume computation. So in this case, what we required is to compute volume for individual polytopes and compute their union. So for example, the network reliability problem, in this case, you have this graphs and some kind of measure for this graph. But what we really need is what are the individual specific counting problems. So in that case, you want to look at what are the possible subgraphs and what are their measure. So you do not really need a volume computation for that case. And in that case, you want to look at the whole solution space of subgraphs, and possibly you want to enumerate over all of them, right? So this volume computation technique will not work here. So what we do there is that we look at the whole space, we partition that solution space by hashing, then we partition to a very small space and enumerate that solution space. And by enumerating on a very small space, we can extend that result for the whole solution space. So that is why we needed a different technique for handling that problem. So such kind of hashing technique could have been useful in the speed vector counting. But the key challenge there was that this speed vector has a very different type of solution space. So what we required there was looking at the actual constant and blasting them to a propositional model counting problem after simplification. So we needed a different technique for there as well. And for the third problem, where we want to count the number of functions, the solution space is totally different. Like we are not computing any models or in volume there. We want to compute how many functions are there. And we needed a completely different technique because the number of function is super exponential, like 2 to the power 2 to the power the number of input space. So we need to do a sampling and then constant counting on top of it. So we needed all different techniques to solve these different questions.
Great, thank you.
Valtteri.
Yeah, thanks for the talk. So I would like to know what kind of computing platforms you used for this, solving these problems, and was it the same platform for all of them?
Yeah, so we needed mostly CPUs. So like we almost use a normal computer, like 32 GB RAM and standard one single processor setup. And all of them were used in similar setup.
Okay.
Are there further questions from the audience? I don't see any hands, so I think we are going to thank the speaker and we conclude the session. So thank you very much.
Thank you.